Hello everyone, this is third lecture, and in this lecture I'll discuss about the boost converter, which is also known as the step up converter that will step up the voltage. So before starting that, I will revise the buck converters that I taken in the last class. So basically in the operation part, I made some mistake, so I will rectify that. So in on state 1, basically the inductor current is smaller than the output current. Okay, so in that case the pre-charged capacitor will also supply to this load. So this load is actually getting current from this side and also from the capacitor. Okay, so this capacitor is getting discharged to this load, and also the input side will supply current to the load. Okay, in on state 2, basically when since this is connected to the input side, so it is linearly increasing. The voltage across this is V in minus VO, which is positive. So the current rising linearly through this inductor. So in on state 2, basically this IL become more than I naught. Okay, so this is a constant current. Okay, so the excess current will flow to this capacitor. Okay, or the ripple current will flow through this capacitor. So in on state 2, basically the capacitor is getting charged. Also load is supplied from the input side. Similarly in off state 1, the inductor current now will decrease because the voltage across the inductor is now minus VO. So negative voltage is across the inductor. So in that case the IL will start to fall. Okay, so in off state 1, actually the IL still remains more than the I naught value. Okay, so the uh, this value, so the excess current will actually flow this capacitor. Okay, and the constant current will flow from this load. So in off state 2, now IL become less than the I naught value. So in that case the stored energy in the capacitor, the load actually will be supplied from this capacitor and from this inductor, because here the current is smaller than the output current and output current is constant. So that current will be supplied from the inductor and capacitor both. Okay, so you should make rectification on the last class. Now I'll start boost converter in continuous mode of operation. So this is the circuit diagram of boost converter, where we are having inductor that is connected in the input side. Okay, then we are having one switch. The basically we are using MOSFET switch for DC-DC converter, because the switching frequency of the MOSFET is higher than other switches. Okay, and we are having diode like this and one capacitor. So these four basic elements we are using to construct the boost converter. If you remember in the last class, in the buck converter also, these four components we have used to create the buck converter. Okay, so this is basically the converter, and this is the input side, and this is the output side. Okay, here actually we are having two modes of operation. One is on state, another is off state. When switch is turned on, that state we will call the on state of the circuit, and when the switch is turned off, that state we will call as off state of the circuit. Okay, so in on state you can see this MOSFET is turned on by applying gate to source voltage, which is normally of 10 to 15 volt. Okay, so once we apply the gate to source voltage to this MOSFET, this is turned on. So in that case you can see that this side output voltage, here it is positive. So arrow side actually it is positive, tail side it is negative. All these conventions we have assumed. This is positive, this is negative. Okay, so you can see that this node actually it is positive, and also once this switch is turned on, so this node actually is at ground potential, so this diode will be in reverse biased. Okay, so in on state you can see that the MOSFET is short circuited and the diode is reverse biased, so it is open circuited. Okay, so we are having these two loops this is the input side loop and this is the output side loop. Okay, so the inductor actually connected with the input side supply. So you can see that the voltage across this inductor will be V in minus VL, that will be equal to 0. So VL actually equal to V in. So positive voltage appear across the inductor. So whenever there is a positive voltage across inductor, so current through inductor will rise linearly. Okay, if you remember that IL was 1 upon L integration V in dt. So 0 to dts on time, we can find what will be the this IL value. Okay, at the same time this circuit is the open circuit. Okay, so output current actually basically supplied from the this capacitor. Okay, so capacitor is getting discharged and it is supplying the constant current to the load. So I naught current is supplied from the capacitor during on state. Okay, similarly in off state the switch is turned off. Okay, you can see switch is turned off, so it is open circuited. Now uh, this diode will be in forward bias mode. Okay, so the energy stored in the inductor and the input supply will give to the this load R. Okay, and at the same time it is charging this capacitor. Okay, so capacitor is getting charged and the load is supplied from the input side. Okay, so both inductor and the stored energy in the inductor and the input side, they will supply to this load. Okay, and capacitor is getting charged in this off state time period. Now what is the voltage across this inductor in that case? So you can see here it is V naught, here it is V in. So voltage across the inductor will be V in minus VO. And also we know that the output voltage is more than the input voltage in case of boost converter. So V in minus VO will be nothing but a negative voltage that is appearing across the inductor. Okay, so current will start falling linearly. Okay, because IL is equal to 1 upon L integration V in minus VO times dt 0 to 1 minus dts. So in that case V in minus VO is negative, so slope is negative. Okay, so linearly it will fall from some maximum value to the minimum value. Okay, so these are the waveforms. From the waveforms you can describe the operation of boost converter. So you can see that VGS we are supplying for dts time, then it remains off for 1 minus dts time. So it completes one time period from here to here. Okay, from one time period, that is dts and 1 minus dts. So again the cycle will repeat. Okay, so these are the periodic waveforms. So IL you can see that during on time it is rising from I min minimum value of the inductor current to the maximum value of the inductor current. Then it will again fall from that maximum current to the minimum current in I1 minus d times ts. Okay, so during on time you can see it is rising from I min to I max. During off time you can see it is falling from I max to I min, and the same cycle will repeat. Okay, and the difference between I max and I min will be delta IL, that will be the ripple in the inductor current. Okay, also if you see here that uh, this average current will be equal to the input average current because they are connected in this series. Okay, so series connection is there, so whatever the average inductor current, that will be the average input current. So average of this will be nothing but I in. Okay, so if you remember in buck converter the inductor was connected towards the output side. In boost converter the inductor is connected towards the input side. So input current become smoothened. Okay, so it is become it is now because of the presence of the inductor, it is you can say it is continuous. Okay, similarly if we want to find what will be the switch currents, so you can see from the figure that during on state the IT will be equal to IL. Okay, during off state IT will be 0 because it is open circuit. So IT is equal to IL during on state and it is 0 during off state, then the same thing will repeat. So from I min to I max, what will be the ripple? The same ripple will appear in this switch current. Okay. Similarly for diode, you can see that during on state it is in forward bias, so it is open circuit. So ID will be 0. Okay, during on state the ID will be 0. Similarly for off state, this diode and this inductor actually they are coming in series. Okay, so ID will be equal to IL during off state. So during on state it is 0. During off state it is nothing but the IL value. So again from maximum to minimum value it is falling. So delta IL will remain the same. So ripple in the diode current will be again delta IL. Okay. Similarly we can draw the capacitor current. So capacitor current you can see from here that during on state IC will be equal to I naught. So it is supplying, that's why it will be minus I naught. Okay, it is discharging, so IC will be equal to minus I naught during on state. During off state basically IC will be IL minus I naught. Okay, so ripple will flow through this capacitor. So you can see that this value actually nothing but IL minus I naught. So from IL during off state, this value we have to subtract I naught value. Okay, we have to take out I naught from this waveform. So we are taking constant value from this waveform. So wave shape will remain the same, but these peaks will shift downwards. Okay, so this will be IL max minus I naught, and this value will be IL min minus I naught. Okay, so the shape you can see that it is of the same shape, but the values will be different. Okay, so it is during on time it is minus I naught, and during off time it is IL minus I naught. Okay, similarly we can plot for the voltages across the switch. So during on state the voltage across the MOSFET switch will be 0 because it is short circuited, it is conducting. Okay, during off state you can see during off state, so if we apply KVL in this loop, okay, or KVL in the outer loop, so VT will be equal to V naught. Okay, so VT uh, minus V naught is equal to 0. So you will find that VT will be equal to V naught. Okay, so during on state it is 0, during off state it is V naught. Similarly we can find what will be the voltage across the diode. So if you see here, so voltage across diode we can find from on state. So in on state, if you again apply the KVL in this loop, okay, so VD minus V naught is equal to 0. So VD again is equal to V naught during on state. During off state it is conducting. So voltage across this will be 0 if we are considering the ideal diode. Okay, so these are the waveforms for ideal components. So ID you can see here, sorry, VD you can see here, we are having this V naught during on state. During off state it is conducting, so voltage across it is 0. Okay, so these are the waveforms, and the explanation you can read from these points. Okay, now again we have to find what will be the ripple in the current. Okay, so this delta IL we can find. So during on state the voltage across the inductor is V in. Okay, so ripple will be, so slope of this line is V in upon L. So from 0 to dts it will reach to I max. Okay, from I min to I max it will reach. So delta I you can find from V in times dts upon L, or the same thing you can find from this. So slope of this line is nothing but V in minus VO divided by L times 1 minus dts. If you multiply we will get minus delta IL. Okay, so if you want to find the magnitude, so delta IL will be equal to, during on time it is V in dts upon L, during off time it is VO minus V in 1 minus dts upon L, and these two things will be same. So if we solve these two, we will get VO upon V in is equal to 1 upon 1 minus D. Okay, where D is the duty cycle which is defined as T on upon total time. Again IL average is nothing but I in, so VO upon V in is equal to 1 upon 1 minus D will be equal to I in upon IO. Okay, so I in we can replace with IO upon 1 minus D. So IL average is nothing but I in, which is equal to IO upon 1 minus D, where IO or output current is defined from the this relationship VO upon R. Okay. Again, if we want to calculate IL RMS, so you can see that the current waveform is similar to that of the buck converter inductor current. In buck converter, the average was I naught, but in the boost converter, the average is I in. Okay. So we can substitute here delta IL square upon 12 plus IL average square. So IL average is nothing but I in square. So in problems, these parameters are given: output input voltages, duty cycles. So based on that, we can find delta IL value. If you substitute here, we can find what will be the IL RMS value. Okay. Similarly, we can find what is IC RMS value. So in IC, you can see for DTS time, it is I naught. So DTS time I naught square, and in off time it is 1 minus DTS, and the value is I in minus IO. Okay. So you can see here this is 1 minus DTS time delta IL square upon 12 plus I in minus IO square. During on time it is D times I naught square. If you take square root of that, we will get the IC RMS value. Okay. Similarly, we can find what will be the ripple in the uh, output voltage. Okay. So during on state, the capacitor was discharging, and it is supplying current to the load, so it was fixed to I naught minus I naught. Okay. During on time it is positive, so either you have to take this area or you have to calculate this area. Okay. You will get the same value for the ripple voltage. So it is easier to calculate from this area because it looks like the rectangle. Okay. So area of the rectangle will be base into height. So this value into this value is known as I naught, and this value is DTS. So if we calculate that area, we will get delta Q value. If we divide by C, we will get the ripple value actually. So delta V naught is equal to 1 upon C, 0 to DTS IC on times T into DT. So this is straightforward. Area will be I naught, this is the height, and DTS, this is the base, upon C, that will give the output ripple voltage. So this is very straightforward to calculate the ripple in the output voltage. Okay. So I naught again we can replace by V naught upon R here. Okay. DTS upon C. So you can see that delta V naught upon V naught DTS upon RC. So here you can see that it is not dependent upon the L value. Okay. Unlike the buck converter. So it is dependent only on the C value and the load. Okay. And TS we can write as 1 upon Fs. So delta V naught upon V naught will become D upon Fs into RC. So if we are having higher value of C, then in that case ripple will be less. Similarly, if we are having higher switching frequency, delta V naught will be small. Okay. So you will find that the switching frequency, basically if it is high, then the ripple will be smaller in all the DC-DC converter cases. Okay. Here the ripple also dependent upon the load. So if we designing DC-DC converter, so we have to keep this into mind. Okay. If load get changed, the ripple in the output voltage will also get changed. Okay. So it is noted that the output voltage ripple is independent of L but depend on the load. When selecting of the value of C, the load condition is considered. The capacitor current ripple is more severe than that of buck converter. It depends directly on the output current or the load. Okay. The selection of L depends on the allowance of peak current of the transistor, the diode, and the inductor. L is also selected to prevent the converter to operate in discontinuous mode. Okay. Smaller value L actually will give the discontinuous mode of operation. So that boundary condition we will study in the discontinuous mode of operation of DC-DC converters. Okay. Again, we can find the ratings of different components. So we are having 4 components. One is a switch, control switch. Then we are having diode. Then we are having inductor. Then we are having the capacitor value. Okay. For voltage ratings, we have to calculate the maximum voltage that is appearing across the device. So across T, you can see from these waveforms that it is V naught. maximum voltage appearing in across it is V naught. So voltage rating we can find directly from that waveform. Okay. Similarly for diode, the maximum voltage appearing across it is V naught. Okay. For inductor, actually it is either VO minus V in or VO. During on state it is uh, VO minus V in, and during off state, sorry, then during off state it was, if you see here, uh, uh, from the inductor. So you can see here during on state the voltage across this is V in, and during off state it is V in minus VO. So we have to take maximum of these values. Okay, which one is maximum we have to take that value. So to make it positive we are taking VO minus V in, because this is the boost converter and VO is always more than V in value. Okay. Similarly for C we can find what is the voltage that is appearing across the capacitor. So it is connected in parallel to the load, so voltage across that will be V naught. Now we can find the average current. Average current actually used for the selection of BJT, thyristor or IGBT based switch. If we are having MOSFET switch, we have to again calculate the RMS value. Okay, so this average value basically useful for selection of the BJT, thyristor or IGBT. Okay, so we can see from these waveforms that so IT actually this value. So this is coming to be I in, because average of IL was I in. So this is I in, but only for the time of, if we approximate this is I in, then it becomes 0, then it is again I in, then again it becomes 0. So if we take the average of that, so dts times I in plus 1 minus dts times 0 divided by total time ts. Okay, so ts get cancelled, so we are getting d times I in. Okay, similarly we can find the average values for D, L and C. So for C it is 0, because average current in that will be 0. L will be I in, that I already discussed. For D you can see here the same thing. For the diode you can see here that it is 0, then it become I in, then again becomes 0. So for DTS it is 0, so DTS time into 0 plus 1 minus DTS times I in divided by total time. Okay, so TS get cancelled, so average value we are getting 1 minus D times I in. Okay, so 1 minus D times I in, that is also equal to IO. Okay, if you remember the relationship, I in upon IO was 1 upon 1 minus D. Similarly we can find what will be the RMS current. So first we have to see the L. So for inductor it was delta IL square upon 12 plus IN square. So once parameters are given, we can find delta IL value. Substitute here, we can find the rating, that is RMS current rating of the inductor. Okay. So similarly we can find what will be for T and for D. Okay, so for T actually this is the same value, but it is for DTS time only. Okay, so this value into DTS plus 1 minus DTS times 0 upon TS. So TS get cancelled, so we are getting D times this value. Okay, so for thyristor for MOSFET switch we are getting the RMS value as D times delta IL square upon 12 plus IN square. Similarly for diode it is for off time only. For on time actually it is open circuit, so it is 0, and off, so DTS times 0 plus 1 minus DTS time. So during on time, so this is the value of the current. Okay, similarly for capacitor the already that I discussed, D times I naught square plus 1 minus D times TS delta IL square upon 12 plus I in minus I naught square divided by TS. So TS get cancelled from here and here also. Okay, so RMS value we are getting this value. Now based on these discussions you can solve this problem. So this is very straightforward problem, and the this answer for this problem is given as this. Okay, so you can solve this problem, you can match your answer. If you are feeling any difficulty that I can discuss in the next class. Okay, so thank you.